Hello and welcome back to another LeetCode video. Today we look at LeetCode 3678. Smallest absent positive greater than average. And we're approaching LeetCode problems interview style here. So we focus on a systematic approach to try to solve the problem, practice communication, and clarity of thought. So that's what we're going to do here as well. Step one, let's understand the problem. So you're given an integer array nums, and we should return the smallest absent positive integer nums such that it is strictly greater than the average of all elements in n. The average of an array is defined as the sum of all its elements divided by the number of elements. Okay, so my first question in an actual interview would be, what is inside nums? Can nums be empty? What are the values inside nums? Can nums be sorted? Is 0 considered a positive number? Because some people think that 1 is the first positive number, which of course it isn't. But it's good to ask that just for clarification. And well, on LeetCode, you can see typically in the constraint section the answers to your questions. But you practice for an interview. Come up with the questions first before you look at the constraints. Right. So, and well, then we're told that nums contains at least one number, and that the value range is positive to and negative numbers. Also given an upper bound for the length of the nums array, but we're going to ignore that. Otherwise, all space and time complexity would ultimately be O of 1, which is of course not very interesting. So for the purpose of an interview practice, we will always assume that there's no upper bound to the input. Otherwise, the analysis is going to be pretty boring. Right, so, and well, also good to ask clarifying questions about the output. And here in the problem description is already pretty clear defined. So obviously we need to return the smallest absent positive integer. So that's just going to be a number. And the next step is now to look at the examples to get a better feeling of the problem. And it's also, I think, a crucial step, especially when you run into more difficult problems. Unless you really work through some examples, the chances that you're going to get stuck later because of an edge case you didn't think about, or because you didn't think your approach through before you started implementing, are very high. So for practicing the process, even if it is an easy problem, you have to dive into the example. So let's just do that now. So here we are given an input array consisting of the number 3 and 5. So computing the average would be, well, summing them up to 8, dividing by 2, because there are 2 elements, so that would be 4. And now we need to find the smallest absent positive integer in nums. Now, that is strictly greater than the average. So our average was 4, so we need to start searching from 5. Is 5 in our array? Yes, it is, so it's not the result. Then I would say we increase 5 to 6 and check if 6 is in nums. It isn't. So that means that's our result. Now what I'm seeing here is that, checking if a number is in our result, if a potential result is in nums, takes linear time unless we turn nums into a hash set. So I'm already thinking about turning this into a hash set so that we have O of 1 lookup time to check if a number is in n. And then we just increase our potential result number by 1 every step until it's no longer in our hash set. Okay, so that already gives us an idea of how a solution might look like. Let's look at example 2. So we're given a nums array that has 3 elements, -1, 1, and 2. So if we sum them up, we get 2. We need to divide it by 3 to get the average. So that's 2 divided by 3. And the next integer that is strictly greater is obviously 1. So we check if 1 is 1 in our nums array, or in our nums hash set if we use 1. It is, so it's not the result. We increase it by 1, and now we check if 2 is inside. It is, so it's also not the result. And then finally we increase this one more time to 3, and 3 is no longer in our nums array or hash set, and that makes it the result. Okay, so now example 3, let's just go through this as well. So the sum would be 3 divided by 2, that would be 1.5. So the smallest integer, positive integer greater is 2. So we check is 2 in our nums. It isn't, so that's why it is our result. Now, looking at this, we see some negative numbers. What if nums consists of only negative numbers? Then our average would also be a negative number, but we need to only return the smallest absolute positive integer. So I guess unless the average is smaller than 0, we start at the average plus 1, and otherwise we start by checking if 1 in our is 0 in our nums array. And I think that would cover all of the cases. So now after going through these examples, I have a pretty clear idea of what I'm going to implement or what I would like to implement. And I think what I'm going to do is I'm going to compute the average just by iterating over all of the elements. And that gives me, and then I compare that against 0 to give me the smallest candidate number to return. Might not be in our nums array. And I would turn nums into a hash set. And then just loop as long with my candidate number until the candidate number is no longer in the hash set. And that makes the candidate number then the result. And that would give me, now because I've spent now the time to analyze the problem, and I now have a clear formulation idea of my implementation solution, I can already also give a runtime space complexity before writing any code. So that would be linear time and linear space algorithm. And I would now ask the interviewer if that's okay if I implemented that. And maybe there's some clarifying questions, but then at one point I'll be given the green flag to continue to implement my solution. So that's what we're going to do now. I like to write the time space complexity on the top usually. And well, the first step that I said was, well, let's compute the average, right? And in Python, we can do that quite easily. So we could just compute sum of all numbers in nums. And we just divide that by the length of nums. That would give us the next integer that is smaller than the average. So it would, if it's 4, it stays 4. If it's 0.6, it would turn into 0. Now, what we also have to do is, well, we have to turn this kind of into a candidate number, right? So let me think. So a candidate number would be, well, actually, we could call it the smallest missing. And that is, of course, the maximum between, now it depends on the definition. Is 0 the first positive integer or no? And if it isn't, then what we do is, well, if 0 is the first smallest smallest positive integer, then we take the smallest missing is the maximum between 1 plus the average or 0, right? Now, I will just turn nums into a set, a hash set, like so. So this will be O of n time and O of n space. The average computing, that's also linear time, but constant space, because we need to iterate over all of the numbers to do that, even when we use a function for us to do that for us. Now we just have a while small is missing in nums, just going to increase it. And in the end, we're just going to return it. So that would be the whole implementation. And of course, you can, write the sum as a loop if you wanted to, but why not use a built-in function? Doesn't take anything away from the solution. And as long as you can explain that this is still O of n time to compute that, right? Okay, so now let's run this through our test cases. And that passes. Now let's submit this to see if it passes all of the test cases. And it doesn't. Aha. Why does this not work? So here we see we have a nums array that contains only a negative number. And we're returning 0 because we assumed that 0 was the smallest positive integer, but the expected one. So clearly in this case, the interviewer does not agree with that agree with us that the smallest positive integer is 0, they think it's 1. So that is why you need to clarify those questions in an interview, even though 0 is by definition a positive number. Right, so I'm going to use this test case. I'm going to run the tests again. And all of them still pass, including the one that failed here. So let's submit this again. Now it passes all of the tests. Yes, so that's a demonstration of why it's really important to ask the interviewer about, the requirements and the assumptions, etc., so that you don't make mistakes like this by just assuming something that the interviewer might see differently. Now, there's another interesting variation of this problem, I would say. What if all of these numbers are in sorted order? What would that change? So that could actually be a follow-up question. Let's pretend nums is in sorted order. Well, to compute the average, we would still have to perform an O of n operation, right? But then to find the smallest missing number that's larger than the average, well, does it change anything for us? Well, what we could do is we could use a binary search to actually find that number, right? So we could, we could reduce the time to find the smallest missing number to a logarithmic problem. And here the trick is, because in the worst case, all of the numbers are maybe from 1 to n in nums, right? So they're 1 to n, something like that. Now, when you compute the average, right? I don't know what the average is. Maybe the average is 5 here. Let's say that is the average. Now, if you were to perform a binary search for the average, you would get here, but then you would still have to do a linear search through the remainder of the array. But you can now, what you can do is you can find this position in log n of the average, but you can then also find where maybe a gap is in those numbers. So if they're all consecutive here, you need to iterate linear through it. However, if you now have a second binary search implementation that finds you the position where difference between elements is larger than 1, that would be also a log n. So essentially what that would do is would turn this array into, let's just make it here where we have 12, 13, 14 here. So the missing one, the next larger one would be 11, right? That would be the number that we would be looking for. And we could turn this array into something where we say 4, where we just turn it into, let me just illustrate it, 5, 7, 8, 9, and etc. So we would now search in this array, and to make a decision of whether to go left and right depends on whether at the current index position we actually have the value of the index in the element at that index. So if we are here at 10, but this is index position 9, we know that the missing value is to the left. If we are at this position, at position 0, 1, 2, 3, and the value is 3, we know that the missing index is going to be to the right here. Otherwise, it would be to the left. So that would also be a log n approach to find where that gap is. So you can actually solve this in a faster time complexity. O of. However, since you need to compute the average, you're not really winning a lot. So you'd have O of n plus log n to find the smallest missing. But you would have O of 1 space. So that's your optimization. You're optimizing the space by not having to build the set. If you were to use one where the nums array was sorted, and you could just do the search. So yeah, And if you see this when you analyze the problem, you know, that would be another good alternative that you could suggest. So even if the array is not sorted, you could sort it in O of n log n time, and you could get away with O of 1 space. That would be a different approach that you could take. And if the array was sorted, you would only need O of n time. The log n is smaller, so it just would be O of n time and O of 1 space. So yeah, so this just to give you some ideas, you know, of coming up with alternative implementations. It's difficult to come up with multiple ones at the same time when you look at the examples for the first time, but you can certainly expect that somebody's going to ask you for something like this, maybe in a follow-up question or something like that.